In this video, I'm going to talk about logical statements. Like the previous video, this video, as well as the next few videos, are introductory in nature, aiming mainly to establish notation and basic results to make things smoother after we introduce the definition of a group. I'd like to begin by reviewing some notation that a lot of you may be familiar with. First of all, when we're writing logical statements, the upside down A-looking symbol means for all or for every, and it's referred to as the universal quantifier. Similarly, the backwards E-looking symbol means there exists, and it's referred to as the existential quantifier. One of the basic building blocks of logic is what's called a conditional statement. Given two logical statements x and y, if we write an x followed by a double bar arrow pointing towards the y, it means if x, then y. You can think about the double bar arrow here as meaning implies that. What the conditional statement is saying is that if x is true, it implies that y is true. Similarly, if we write x followed by a double bar arrow with both a left and right hand arrowhead and then a y, that means x if and only if y. In other words, it means if x is true, then y is true, and if y is true, then x is true. This is what's called a biconditional statement. Sometimes we also abbreviate if and only if by IFF, but I tend to avoid doing this in case some people forget to notice the extra f, or maybe think it's a typo or something. In any case, I usually like to spell out if and only if, but sometimes I might also use IFF just to save space. Finally, if we have some logical statement x and we write a tilde followed by x, that's what's called the negation of the statement x, and it simply means not x. So if x is true, then not x is false, and if x is false, then not x is true. Now let's look at a couple of examples of how to use this notation. First of all, let's suppose that a and b are sets, and let's try to express the definitions of a is a subset of b and a is not a subset of b using the logical notation that we've just introduced. According to the definition given in the previous video, a is a subset of b if and only if every element of a is also an element of b. It's very easy to write this out using logic notation. A is a subset of b if and only if, for every element little a in A, we have that little a is also an element of b. In the previous video, we also mentioned that for a to not be a subset of b is equivalent to saying that there's at least one element of a which is not an element of b. In logic notation, we have that a is not a subset of b if and only if there exists an element little a in A such that little a is not in b. Now, just to save space, a lot of times we're going to abbreviate such that by ST. This is a pretty commonly used abbreviation. For the next example, let's consider this logical statement, and let's try to decide whether or not it's a true or false statement. Using the definitions of the universal and existential quantifiers, the statement says that for every integer n, there exists a rational number x such that x minus n equals 1. Think about whether or not you think this statement is true. Is it true that for every integer n, there is a rational number x with the property that x minus n equals 1? Well, of course, this is true, because whatever integer n is chosen, we can always take x to be n plus 1. If n is an integer, then x is also going to be an integer, so it's certainly going to be a rational number. And by construction, x minus n is going to equal 1. Now, let's think about what happens if we reverse the order of the quantified statements in this example. In other words, let's consider the statement, there exists an x in Q, such that for every n in Z, x minus n equals 1. Do you think that this statement is true? In other words, is there a rational number x with the property that, for every integer n, that rational number minus n equals 1? Of course, there's no way that this can be true. For example, if x is a rational number, then we can always take n to be the smallest integer which is greater than or equal to x. Then x minus n is guaranteed to be less than or equal to 0, so it's definitely true that x minus n is not equal to 1. The important point here is that when you're writing quantified statements with multiple quantifiers, the order in which you list the quantified statements can and usually does make a difference. Next, I'd like to mention a couple of facts The first fact is that the conditional statement if x then y is logically equivalent to the conditional statement if not y then not x. In other words, if one of these conditional statements turns out to be true, then they're both true. And if one of them turns out to be false, then they're both false. However, in practice, sometimes it may be more obvious why one or the other of these statements is true or false. The statement if not y then not x is called the contrapositive of the statement if x then y. To give a couple examples of how the contrapositive can be used to prove or disprove a conditional statement, first consider the statement if n is a natural number, then n is a rational number. This is a conditional statement, and we can write it using our notation as if n is an element of n, then n is an element of q. Now, I think we all probably realize that this is a true statement, but if for some reason this weren't obvious to us, we could also consider the contrapositive of the statement. The contrapositive of the conditional statement is the statement that if n is not an element of q, then n is not an element of n. This is certainly a true statement, because if n is not a rational number, then there's no way that it could be a natural number. For me personally, the original conditional statement seems slightly simpler than the contrapositive in this case, but the point that I'm trying to make here is that the original statement and its contrapositive are logically equivalent. Once you know that one of them is true, you know that they're both true. To give another example like this, consider the conditional statement, if x is a real number, then x is a rational number. The contrapositive of this statement is the statement that if x is not a rational number, then x is not a real number. This time both statements are false, but to me, psychologically, it's a little more obvious that the second statement is false, since I can think of examples of numbers x, like the square root of 2, which are not rational, but which are still real. Anyway, the point of these examples is just to remind you that a conditional statement is always logically equivalent to its contrapositive. But in practice, one of the two statements may seem easier to prove or disprove when you're trying to write a formal proof. The next pair of helpful facts that I'd like to mention are related to negations of universally and existentially quantified statements. First of all, consider the negation of the statement for every x in A, statement x holds. It turns out that the negation of this universally quantified statement is equivalent to the statement that there exists an x in A such that the negation of x holds. If you think about it for a minute, you can convince yourself that these two statements are equivalent. First of all, if the statement inside the parentheses here happens to be true, in other words, if for every x in A statement x holds, then that means that there are no x's in A for which the negation of x holds. In other words, it means the existential statement in the bottom here is false. On the other hand, if the statement in the parentheses on the top is false, then it means that there is at least one element x in A for which statement x is false. That's precisely the bottom statement, that there exists an x in A such that the negation of x holds. It's also a good idea to stop for a minute and think about what this means practically. If you're trying to prove that a universal statement is true, then you have to show that for every x in a certain set, some statement holds. On the other hand, if you're trying to prove that a universal statement like this is false, which is the same as trying to prove that the negation of the statement is true, then all you have to do is show that there's at least one x in the set A with the property that the statement big X is false. The x that does that in the second case is called a counterexample to the original universal statement. Now similarly, if you're trying to prove an existential statement, like the statement that there exists an x in A such that some statement capital X holds, then all you have to do is find an example of a little x in A for which the statement is true. However, if you're trying to prove that that existentially quantified statement is false, in other words, if you're trying to prove that the negation of the statement is true, then what you're trying to prove is equivalent to the truth of the universal statement for every x in A the negation of x holds. It's actually not difficult to deduce the equivalence of these two statements from what we already said about the negation of universally quantified statements on the previous slide. To make sure that we understand this, let's take a look at a couple of examples. First of all, here's the logical statement that we saw earlier in the video. This is the statement that there exists a rational number x such that for every integer n, x minus n is equal to 1. We convinced ourselves earlier in the video that this is a false statement. But let's just clear our minds and look at it again. Think about the quantity that I've written in parentheses here as the statement x. This is an existential statement, and we suspect that it's false. One way that we could try to prove that is by looking at the negation of the statement and proving that the negation is true. The negation of the existential statement, there exists an x in Q such that x holds, is the universal statement for every x in Q, not x holds. X itself is the universal statement that for all n in Z, x minus n equals 1. Therefore, the negation of x is the existential statement that there exists an integer n such that x minus n is not equal to 1. Now, last time we talked about this problem, we convinced ourselves that the statement in green here is actually true, because for any rational number x, we can just take n to be the smallest integer which is greater than or equal to x. That guarantees that x minus n is less than or equal to 0, and so it's definitely not equal to 1. That proves that the statement in green at the bottom, which is the negation of the original statement, is true, and therefore the original statement must be false. As a final example, let's try to prove or disprove this quantified statement. This is the statement that for every real number t, there exists an integer n such that n times t is greater than t. If we call the statement in parentheses here x, then this is the universal statement that for all t in R, statement x holds. Now, I could just show you the answer, and maybe some of you already figured out whether or not this statement is true or false. But there is some thought process that goes on behind the scenes or even subconsciously, and I first want to try to unpack at least a little bit of that so you can see one way to think about this problem. If you're confronted with a statement like this and you don't have any idea what to do, what you could do is first try some examples. In other words, first choose some values of real numbers t and see if for those values you can prove that there exists an integer n such that n times t is bigger than t. As you're doing that, think about what's going on, but also remember that no matter how many individual values of t the statement holds for, it's not going to actually prove the universal statement is true unless you can show that it's true for every real number t. In other words, testing out individual values of t is a good strategy for trying to understand what's going on, but it's not quite enough if you're trying to prove that a universal statement is true. In order to do that, you would have to prove that it's true for every value of t. Now, on the other hand, if it turns out that we can find even one value of t for which statement x is false, that value of t will be a counterexample to this universal statement, and that will show that the universal statement is false. So let's go ahead and try this out and see what happens. First of all, maybe you could try taking t equals 1, but pretty soon you're going to realize that if t is any positive number, you can always choose n to be the integer 2, and then it's definitely going to be true that 2 times t is bigger than t. Now, on the other hand, that same value of n is not going to work, for example, if t is negative 1, because then it's not true that negative 2 is bigger than negative 1. The inequality goes the other way. But if you think about it, if t is a negative number, then if you took n to be negative 1, n times t would be a positive number, so n times t would be bigger than t. Now, even though this is looking pretty good, and we've shown that statement x is true for almost every possible value of t, there is still one value of t which is not covered by the previous two cases, and that is when t is equal to 0. Now, it's pretty clear that when t is equal to 0, no matter what integer n you choose, n times t is also going to be equal to 0, and it's never going to be true that 0 is strictly greater than 0. The point here is that statement x actually fails, so we've found a value of t for which statement x turns out to be false, and that means that this universal statement is going to end up being false. Now, when I turn this problem in, I wouldn't want to show all of my mistaken attempts here. So I would probably try to clean it up and make it look more logical, something like this. I'm aiming to prove that this universal statement is false, so I will consider the negation of the statement, which is the existential statement that there exists a t in R such that the negation of x holds. Since x is the existential statement that there exists an n in Z such that nt is bigger than t, the negation of x is the universal statement that for every n in Z, the negation of nt bigger than t holds. The negation of the statement that nt is greater than t is the statement that nt is less than or equal to t. So now I've arrived at the statement, there exists a t in R such that for every n in Z, nt is less than or equal to t. And I know that this statement is the negation of my original statement. Well, is there a real number t with the property that for every integer n times t is less than or equal to t? If you followed our thought process from before, then you can probably see right away that there is. And here's the proof. Let t equal 0. Then, for every integer n times t is equal to 0. So nt is less than or equal to t. Since we proved that the negation of our original statement was true, that means that the original statement itself is false. In this example, we disproved the original universal statement by finding the counterexample t equals 0. Well, that's the end of this video. There are going to be 3 more introductory videos before we talk about the definition of a group. In the next video, we're going to talk about set operations.